Well, welcome everyone. We're very happy to have Pierre-Alexandre Arlove from Strasbourg, who's going to talk about contact non-squeezing.
Okay, thank you very much, Royal, for the invitation and presentation. I'm really happy to be here. It's a real honor to present some of my work today. So yes, today I will talk about contact non-squeezing in various closed prequantizations. And I will start the talk by talking about what happens, the context a bit in symplectic geometry, and then move to what happens in contact geometry, and more precisely for contact manifold that are prequantizations. So that are a special type of contact manifold that are S1 bundle over symplectic manifold. Okay. So yes, in symplectic manifold, it's very well known, I think, that you don't have any local invariant, but interesting global invariant quantities can be deduced once you have a symplectic form. So more precisely, if you have any symplectic manifold, so W a manifold endowed with a closed non-degenerate to form omega, for any point P, there exists a neighborhood of this point such that in this neighborhood, your symplectic form just looks like the standard symplectic form in R2n given by the sum of dxi veg dyi. So locally, every symplectic form looks the same, every symplectic manifold looks the same. And so the natural question is, can we deduce from a symplectic form interesting, not local invariant quantities, but at least global invariant quantities? And the first answer to this question, so there is a trivial global invariant quantity that you can deduce once you have a symplectic form, is a volume form. So you have a symplectic form omega, you put it to the power n, so omega, veg omega n times. Actually, you get a volume form because omega is non-degenerate. And if you have a diffeomorphism that preserves the symplectic form, so a symplectomorphism, it will also preserve this volume form. So volume, you will be able to deduce volume invariant, which is a global invariant quantity. And then the natural question is symplectic geometry more interesting than volume geometry? When you have a symplectic form, can you deduce most interesting global invariant? And I think maybe, oops. Okay, so so the answer is yes. And the most, I think, beautiful theorem that illustrates it is a theorem of Gromov, or the non-squeezing theorem that he found in the 80s, so 1985. That says that if you have a symplectic embedding of a symplectic ball of radius little r inside a cylinder of radius big R, then you can find such embeddings only if the radius of the ball, so little r, is less than big R. And if you were only considering volume preserving diffeomorphism, then it will be easy to send the ball inside the cylinder by a volume preserving diffeomorphism, since the cylinder is of infinite volume and the ball is of finite volume. So with symplectic geometry, you can really measure things, like you can have a global invariant quantities that are really more precise than volume quantities. Yeah. Okay, so now let's turn to what happens in contact geometry. If you have no questions, of course, stop me. So first, the definition of contact manifold. You have a manifold M endowed with a distribution of hyperplane. So today I will only work with co-oriented contact distribution. That means that you have a vector field that is everywhere transverse your contact distribution, so distribution of hyperplane. And moreover, the distribution of hyperplane is required to be maximally non-integrable. In other words, it means that if your distribution of hyperplane is given by the kernel of a one form alpha, then the exterior derivative of alpha restricted to this distribution of hyperplane is non-degenerate. In some sense, the alpha is a symplectic form restricted to your to the contact distribution. And okay, but today we are really interested, like the geometric structure we are interested in is the distribution of hyperplane, not the one form alpha. So we will look at diffeomorphism that preserve the contact distribution, but not a specific one form. But yes, some remark because we will talk about this vector field later. So, but once you fix a contact form, so one form whose kernel is the contact distribution, then you get automatically a vector field called the rep vector field associated to alpha, which is uniquely defined by these two equations. Okay, so d alpha that you evaluate on this vector field is constantly equal to 0, and alpha evaluated at R alpha is constantly equal to 1. And some example of a contact manifold before saying what are the local and global invariant quantities that maybe we can extract from a contact distribution. So if you start with an exact symplectic manifold, so for example, cotangent bundle, then if you take the product of this symplectic manifold with the real line or with the circle S1, you get automatically a contact distribution by looking at the kernel of the one form bz minus lambda, where z is the coordinate on R. Okay, so, and the second type of contact manifold are a special kind of prequantization, okay? It's a trivial S1 bundle. I will give formal definition of what is a prequantization, but this is one kind of prequantization. Not exactly the kind of prequantization we will look at today, because we will look at closed prequantization. Here, this is open, but it is a trivial S1 bundle, and we will look at non-trivial S1 bundle over simplification. Okay, so in contact geometry, we have the same kind of non-existence of local invariant as in symplectic geometry. So more precisely, if you have a co-oriented contact manifold, then for any point in your manifold, there exists a chart such that in this chart, your contact distribution looks like the standard contact distribution in R2n plus 1. So given by the kernel of the one form bz minus the sum of yi dxi. So here I've put a picture of this standard contact distribution when n is equal to 1. So in R3. Okay, so no local invariant, and here the situation is even more, let's say, flexible or dramatic than in symplectic geometry, because you don't have like trivial global invariant quantity that you can deduce once you have a contact distribution. So just a distribution of hyperplane, it's not easy to deduce from it some global invariant quantity. For example, this can be illustrated, let's say, by this lemma in R2n plus 1, so the standard contact manifold of dimension 2n plus 1. You can squeeze any ball as large as you want inside a neighborhood of 0 as small as you want by this diffeomorphism, because this diffeomorphism preserves the contact distribution. So what is this contactomorphism? It sends x, y, z to ax, ay, a square z, where a is just a positive number. So when A is very small, you can squeeze very big bounded set inside a neighborhood as small as you want of 0. And so with the theorem and this lemma, you have a corollary that you can squeeze any ball. So you take a Euclidean ball of radius as big as you want, you would be able to find a contact embedding of this ball inside your contactor manifold M. Because locally, M looks like R2n plus 1, and in R2n plus 1, you can have all the squeezing that you have. So if we want to extract the global invariant quantities or to expect some non-squeezing phenomena, we will have to be a bit more careful about what we define non-squeezing. And this is okay, so here what I define is not non-squeezing, it's more like squeezing. So, And here I state the definition first. So I will say that a bounded set U can be contactly squeezed in a set V inside a contact manifold M if there exists a contact embedding of U inside V that can be extended to a contactomorphism that is isotopic to the identity of the ambient contact manifold M psi. So here the big difference with symplectic geometry, what I'm asking is that everything happens in an ambient contact manifold, okay? So I fix an ambient contact manifold M psi, and I say that a bounded set U can be contactly squeezed in V inside this manifold M psi if there exists this embedding that can be extended to the whole contact manifold. And moreover, I ask this contactomorphism to be isotopic to the identity.
So in this case of local charts, by this definition, any large ball can be contact squeezed inside any ball, taking M to just be the whole Euclidean space? Or
no, so I think you're talking about the corollary here. No, here I'm just...
Because that map extends to a global contactomorphism, right?
So this squeezing, yeah, here I'm just talking about contact embedding. Yeah, and then even this ball lives in the Euclidean space.
Yeah.
And this is just an abstract contact manifold.
So he's asking in lemma, like this lemma is isotopic to identity.
In the lemma.
Yeah.
Sorry. Yeah, in this lemma, it is even isotopic to the identity.
Okay.
Yes. Yeah.
So by your definition, you could say that a ball of any radius R inside R2 n plus 1 contact squeezes inside a ball of any other radius.
Yeah. You're right.
By using this.
Yeah, because this is isotopic to the identity, and
Okay.
And you can even make it compactly supported, actually. Because your ball is bounded, then you look at the image, and then you take cutoff function, and
okay.
So yeah. Okay. And so what happens about non-squeezing? Actually, with this definition, there exists some non-squeezing phenomenon. And the first one was discovered in the contact manifold R2n times S1. So here S1, so my circle S1 has length 2 pi, okay? It's a normalization, but it will appear in the theorem. So and it's the standard contact form, the standard contact structure on R2n times S1 that is given by the standard contact distribution on R2n plus 1 that descends to a contact structure on R2n times S1.
Okay. So this theorem is not true if you replace the S1 with the real line from what we just said.
Yeah, exactly. Yeah, here this topology S1 is important. Yeah. So in R2n plus 1, you can squeeze everything, but in R2n times S1, it won't be possible anymore. Thanks to this theorem of Eliashberg, Kim, and Polterovich. And they say that the contact ball, so a ball times S1 of radius big R, cannot be contactly squeezed inside the cylinder times S1 of radius little r inside the ambient contact manifold, which is R2n times S1, if there exists a multiple of 2 pi between pi little r square and pi big R square. Okay. And so some remarks. So yes, a first difference with symplectic geometry is that we have a more restricted definition of what we call squeezing. And also here there is this 2 pi that we didn't have in symplectic geometry. But this 2 pi actually is very important because if you take pi big R square and pi little r square to be strictly less than 2 pi, then you can squeeze everything. Okay. So this 2 pi here is important. And what other remark I wanted to make? Yeah. So similar results were found also for other contact manifold, which are of the type W times S1, where W is a Liouville manifold. So some special kind of exact symplectic manifold. And today we will have this kind of result, but for closed contact manifold that are S1 principal bundle over a symplectic manifold. So here W times S1 is open, and we have the same kind of the same kind of result, but for a closed S1 principal bundle.
I have one more question.
Yeah.
In the definition of contact squeezing, is there any reason that the first subset has to be bounded? How to be unbounded or something? Or
Okay, why I've said bounded in my definition? I think I've said bounded so that you can make this contact isotopy compactly supported. This is what I had in mind when I've written the definition.
oh, okay.
Because here actually cannot be contactly squeezed. Yeah, it cannot be contactly squeezed by a compactly supported contact isotopy. Yeah, maybe.
Oh, I see. So
Yeah.
if you're squeezing a bounded subset, then you can have a stronger condition. You want the embedding to extend to a compactly supported.
Yeah.
Okay.
So this is why I put bounded, I think, when I've written the definition. And yeah, maybe you could write the definition without this bounded also, it would make sense. And yeah, well, at least this is what I had in mind when I written it. I'm not sure if there are problems if you forget about the bounded.
Okay.
Okay. So, okay, so what is a prequantization? So a prequantization is a special kind of S1 principal bundle, M over W, that comes with a connection one form, alpha, such that the kernel of alpha is a contact distribution. Okay. And some remark about this definition, maybe, yeah. So the rep flow of alpha, with this definition, it's a consequence, it will induce this S1 action. Okay, and here S1, I take the same normalization. So the length of S1 is 2 pi. So it means that the rep flow of alpha will be periodic of period 2 pi. So if you take any, the orbit of any point will be of minimal period 2 pi. Okay. Another consequence of this definition is that the curvature form, so the curvature on the two form on W, such that the pullback is d alpha, is a symplectic form. And maybe an interesting remark for us also, so once you have a prequantization, actually you have a whole sequence of contact manifold. So if you see Zk, so the cyclic group of order K, you can see it as the kth roof of unity inside the circle S1. So since S1 acts on M, Zk also acts on M, and the quotient manifold is what I call the Mk. And Mk, so the contact distribution psi on M also descends to a contact distribution on Mk. And the contact form alpha descends to a contact form alpha k on Mk. And maybe something that is interesting for us is that the rep flow of alpha k will also be periodic, but the minimal period will be of 2 pi divided by k. Okay, so.
And so these are not contactomorphic, or they are?
Which
the M and the M sub k?
No, I think they are not even usually diffeomorphic.
Oh.
No, because let's say M is, how do you say that? M is, I forgot the name. Like when the pi 1 is equal to 0, is, Okay, the next example is like that. Like the pi one is 0, so for the sphere. Then when you quotient by zk, you get length spaces, and each length spaces is different. So pi one is 0.
Oh, okay.
Yeah, no, okay, I forgot the. So yeah, so usually they are not even diffeomorphic. So, and yes. So yes, first example, the sphere. You take the sphere S2n plus 1 inside R2n plus 2. You can see it as a subset of the complex numbers to the power n plus 1. And then you have a natural action of S1 on the sphere just given by the multiplication by exponential it. And yes, so if you quotient the sphere by this S1 action, you get what is called usually complex projective space. And when you quotient by the action of zk, you get what you call length spaces, okay? And so for k is equal to 2, you get the real projective space. So you quotient the sphere by plus or minus. And the connection one form here, so the contact form, if you want, is given by the one I'm taking is the sum of xi dyi minus yi dxi. And it induces the standard contact distribution on the sphere. Okay, so second example. So this, maybe I go a bit quick. So if you take any contact manifold that admits a contact form whose rep flow is 2 pi Zoll, what I mean by 2 pi Zoll, I mean that the rep flow is periodic of minimal period 2 pi, and each point has orbit equal to 2 pi, okay? So the orbit of any point is the same, equal to 2 pi. Then if you quotient m by this rep flow, you get a prequantization. Okay. So I state, so before stating the main theorem, I just recall a bit the context. So I will work with a prequantization bundle. So M is a S1 principal bundle over W with a connection one form alpha such that the kernel of alpha is a contact distribution. And omega is the curvature form associated to alpha, which is a symplectic form. And the prequantization I will work with will be either the sphere over the complex projective space that we have just described, or M with the contact distribution given by the kernel of alpha is a closed contact manifold and is strongly orderable contact manifold. And this I did not define what is strongly orderable. I will define it during the talk. And I will give some examples of strongly orderable just after stating the theorem. But let's say it's a natural assumption in contact geometry. It has become natural now. So orderable, the first definition of orderable contact manifold was given by Eliashberg and Polterovich. It's that there exists a partial order on the universal cover of the group of contact homomorphism. And strongly orderable is a condition that is a bit stronger than that we will see during the talk. Okay. And so some notation here. So what I will call a contact ball. So when we had a trivial S1 bundle, it was easy to talk about what is a contact ball. Here it won't be so hard, but what I will do, I will start with a symplectic embedding of a ball of radius big A. So inside the Euclidean space into my symplectic manifold W omega. And then the contact ball. So I have a symplectic embedding here, W. And then, over W, I have my prequantization bundle. So let's say pi, here psi, and here I have a covering map. So M over K. So this is a covering map. And then I have another projection here, and everything is commute. So this is, I think, what I've written by K. So what will be a contact ball of radius A? I take a symplectic embedding of the ball of radius A, and then I lift it to MK. Okay, this is what I've written BK little a. And the theorem is the following. So if, okay, you take two radius, big R and little r, if there exists a multiple of 2 pi over k between pi little r square and pi big R square, then you know that the contact ball of radius big R cannot be contactly squeezed in the contact ball of radius little r inside the ambient contact manifold MK psi k. Okay. And so maybe some comments. So this is a bit technical assumption. So we will see maybe during the proof why I need this technical assumption that little r is small enough with respect to my first symplectic embedding, so to A. But this is just technical remark, so maybe we don't care too much about it. But maybe what is interesting to note here is that more K gets big, and more I can detect non-squeezing phenomena. Because more K gets big, more I will have a multiple of 2 pi over K in this segment. Okay? So this is maybe an interesting remark. Of course, this kind of squeezing can be done if we look at only diffeomorphism. Okay, so if we look at diffeomorphism isotopic to the identity, it is possible to send this ball inside this ball. It's really the contact structure, so the distribution of hyperplane that make it impossible to do so. Okay, so in some sense, you can have global invariant quantities from this theorem. And yes, so maybe.
I see. So if K is small, it becomes harder to do contact squeezing?
No, let's say if K is small, then you can, let's say if K is equal to 2.
Yeah.
For example, then you're in the case of real projective space. Let's say this is 0 pi a square. Let's say this is, I think you can choose A such that this is equal to 2 pi. So or what I want to say, yes, yeah. Okay, so you can, there are symplectic of a ball of radius square root of 2 inside CPN with the convention. Okay, so you can start with a symplectic embedding like that. Then you have 2 pi over 2, which is here.
Yeah.
And then if you take a ball with radius here, okay, I have to take this radius to be less than pi. This is a bit the technical assumption. Okay, so if I take a ball with radius here and a ball with radius which is greater than 2 pi over 2, then this ball cannot be contactly squeezed inside this one. But I can see only, let's say in some sense, one non-squeezing. For balls that are with radius here, I know that I cannot squeeze this kind of ball inside balls here. But if K becomes greater and greater, then I have more and more multiple of 2 pi over K. So a ball which is here is not the same as a ball which is here, which is here. Like I can distinguish more and more balls.
I see. Okay.
This is why I was saying like more K becomes big and more you can do precise measurements.
Yeah. Oh, okay. So if you take big R and little r fixed,
Yeah.
as K becomes as K gets big, this obstruction vanishes.
The what?
As K gets big, then the obstruction vanishes or something, because eventually you can find some some J.
I think,
So since the obstruction vanishes for large K, then I guess it's easier to embed or to context squeeze for large K. So it's harder to context squeeze for small K.
no,
That's the opposite, yeah?
no, that's the opposite. What you mean that the obstruction vanish?
Yeah, I think I have my thing.
You see 2 pi divided by k is.
The obstruction appears when K gets big.
Yeah, exactly. More K gets big and more you have obstruction.
Yeah.
Then you can distinguish this ball from this ball, this ball from this ball.
Okay.
Okay.
Thanks.
And
After sign, you were right.
Yeah, I'm mixing up the words can and canon.
okay, this is in some sense, it's kind of when K goes to infinity. This is very heuristic. When K goes to infinity, you get CPN because you get the whole circle. And in CPN, you cannot squeeze because you are in symplectic geometry. In some sense, no? More K, if K goes to infinity, then you just quotient by S1 and you get. But yeah, this is a bit heuristic. Okay, so no questions? And then just quickly some example maybe are strongly orderable. Even if I didn't give definition, I give some example and then I will give, the definition later during the talk. So if you start with a closed Riemannian manifold whose geodesic flow is 2 pi Zoll, so it's periodic and the period of any point is of the same minimal period 2 pi, then the unitary cotangent bundle of this Riemannian manifold is a contact manifold that admits a rep flow which is 2 pi Zoll. So it is a prequantization, and moreover, Colin, Chantraine, and Dimitroglu-Ritzel have shown that this contact manifold is strongly orderable. Okay, and the tools involved is symplectic geometry, symplectic homology, sorry. So this contact manifold admits a UV filling whose symplectic homology does not vanish. And this is how they deduce that it is strongly orderable. Okay, but this is a bit technical, but at least maybe you hear a bit keywords of what are the tools used to show this kind of theorem. And so what I mean by, so this kind of contact manifold, when you quotient this kind of contact manifold by the action of ZK, you can apply the previous theorem to this kind of contact manifold. Another kind of contact manifold where you can apply the previous theorem. So you start with a closed symplectic manifold, which is integral, in the sense that when you evaluate omega on the H2, you get multiple of 2 pi. Okay. To any such kind of symplectic manifold, you can associate S1 bundle whose Laplace projects to omega over 2 pi by this map that associate to element in H2 with coefficient in Z, with H2 with coefficient in R. And this S1 principal bundle admits a connection 1 form whose curvature is exactly omega. And this will be a prequantization. Okay, this is a standard procedure. And if you assume, moreover, that the evaluation of omega over pi 2, so the sphere of W is 0, then results of Colin, Chantraine, Dimitroglu-Ritzel again show that this contact manifold is strongly orderable because this manifold will be hypertight. It means that the periodic, this contact form alpha actually, the periodic orbits of alpha will be non-contractible. And okay, so this is another kind of contact manifold that fits the assumption of theorem. So if you take quotient of this M, it fits the previous theorem. Okay.
If If the base is, if omega pairs to 0 with pi2 in the base, that doesn't mean that the bundle is trivial.
No.
No.
No. For example, if you take W to be a surface which is not a sphere, then no, you have non-trivial S1 bundle. Yeah. No, it's non-trivial. Why it's non-trivial? Because the chain class is non-trivial, no? The chain class is a symplectic form. So yeah, it will be trivial even only if the chain class is 0. Yeah. And here the chain class is non-zero.
So just to understand, what you wrote above for the first part of number 2 is just a definition of a prequantization bundle.
Yes, I think so. Yes.
And then with this extra condition, it becomes strongly orderable that you're symplectically
Yeah, this is let's say a standard construction. When you have an integral symplectic manifold, you can always associate to it a S1 bundle whose curvature, whose connection one form is exactly this symplectic form.
Okay. No. I guess maybe I'm asking another silly question, but is there, or I guess what is your definition of prequantization? Because I guess my internal definition was a contact manifold that arises from exactly this construction.
Yeah. I think every prequantization arises like this.
Oh.
You're right. This was not my definition of prequantization,
Yes.
but I think they are equivalent.
What was your definition of prequantization?
It was an S1 bundle, principal bundle, M over W, that admits a connection one form, alpha, whose kernel is a contact distribution.
Oh, okay.
Yeah, but yes, I think any prequantization, as I said, has to be of this form.
Yeah.
Mm.
Right. Yeah. Because if the kernel is a contact distribution, then the curvature has to be non-trivial. So
Yeah, it's symplectic and
okay.
Yeah. Okay. If no more question, maybe I try to give some ideas of the proof. So yes, to prove this theorem A, I will construct a contact capacity and just some notation. So I will say that the T integer part of a number X is the smallest multiple of T, which is greater or equal to X. Okay, this is some notation. And then the contact capacity is the following. So I say that there exists a map, so this is what I call the contact capacity, that associates to open sets of NK a real number, okay? Non-negative real number, eventually a plus infinity, such that it is monotone with respect to inclusion, so the capacity of U is less than the capacity of V if U is included in V. The 2 pi over k integer part of this capacity is invariant by contactomorphism isotopic to the identity. And then finally, to estimate. So if I take a contact ball, again, what I mean by a contact ball, I fix first a symplectic embedding, and then I lift. So then the contact ball here, and then I lift this ball to MK. So the capacity of a ball of radius little r is less than pi r squared. And again, I have this a bit technical assumption if R is not too big. And the capacity of a contact ball is greater or equal, so to estimate. Okay, and yes, so believe me, with this theorem, it's very easy to get theorem A. Just if you assume that you can send a big ball by a contactomorphism into a small ball, contact ball, then by the first property, the capacity of the image of the big ball will be smaller than the capacity of the small ball. But at the same time, the capacity, the 2 pi over k integer part of the image of the big ball has to be the same as the 2 pi over k integer part of the capacity of the big ball because of 2 pi over k invariance. Invariance by contactomorphism, and then you use these two estimates to have a contradiction. Okay, so and but how to construct this capacity actually? And very heuristically, and then the aim would be to make this a bit more precise. So the capacity of a domain U measures to which extent a contact isotopy supported in U can translate a point in the red direction. Okay, so this is heuristic, so we have to define what is the translation of a point in the red direction and things like that, but this is a bit the idea. And so what is a translated point and translation of a point? So you start with a contact, let's say closed contact manifold, and then, okay, now I'm working in the universal cover, the group of contact homomorphism, but why so? It's because, as I said, I will look at contact isotopy, and then I will associate to contact isotopy some number, some translation of a point. But actually, this number won't depend on the whole contact isotopy, but only on the homotopy class of this contact isotopy. So if I have another contact isotopy, which is homotopic to the first one relatively to endpoints, it will give the same number. And so I will work in the space of contact isotopies up to homotopy relatively to endpoints, and which is exactly what I denote by universal cover of COM tilde. Okay. And I will say that before this defining translated point, I define what is a discriminant point. So a discriminant point is of a contact isotopy to homotopy is a fixed point of the time one of this contact isotopy. And moreover, at this point, the time one does not preserve only the contact distribution, but also preserve the contact form, okay? And actually, this definition does not depend on the contact form. It's easier and more convenient to define it like that, but actually there is a way to define this discriminant point without requesting any contact form, but only the contact distribution. And then translated point, this notion does depend on the red vector field, so on the one form, alpha. So a point will be said to be a translated point of phi tilde with translation big T if X is a discriminant point of the red flow at time minus T composed with phi 1. Okay, so in particular, phi 1 of X will be translated in the red direction of amount T. Okay, it will be translated by T in the red direction. And then a last notation, I will talk about the spectrum of phi tilde to be the set of all numbers T such that phi tilde has a translation, as a translated point of translation T. And so why maybe we call it spectrum? Let's say a good reason maybe it's the spectrum is nowhere dense. Okay, maybe you could expect that spectrum would be discrete. It's not always the case. It's not always discrete, but at least it is nowhere dense. And also, as I said, this notion of discriminant point is natural. So this is also a natural property of discriminant point. So X will be a discriminant point of phi tilde if and only if psi 1 of X is a discriminant point of the conjugate of phi tilde by psi tilde. Okay, so some lemma that might be interesting for later, if we have time to go into proof. Okay. And so now there is theorem C. So theorem C is that we are able to construct maps, actually, that associate to a contact isotopy a number of the spectrum. Okay, and I call this kind of map spectral selectors. So, and then from theorem C, we will deduce theorem B, and from theorem B, we can deduce theorem A. So from theorem C, we will be able to construct contact capacity. So more precisely, what is this theorem C? You start with a prequantization, which is either the sphere over a projective space, as we have described, or a closed, strongly orderable prequantization. Then the theorem says the following, that there exists a map that associates to an element of the universal cover a number R, which will be a translation of a translated point of phi tilde. And this map we have also other very nice algebraic properties. So one of them is triangle inequality. And so C of psi phi is less than C of psi tilde plus the 2 pi over k integer part of phi tilde. This triangle inequality becomes even better if you ask psi tilde to be a path of strict contact homomorphism. So it preserves not only the contact distribution, but also the contact form. It is compatible with some, let's say, this binary relation. For the moment, we don't know that this binary relation is a partial order, but actually it is. But so you say that phi tilde is less than psi tilde in some sense if you can represent phi tilde by the contact isotopy whose Hamiltonian function is less than the Hamiltonian function of psi tilde. Okay. And if you have this kind of condition, then C of phi tilde is less than C of psi tilde. C of the identity is equal to 0. Some non-degeneracy property also. So if phi tilde is greater than the identity and phi is not equal to the identity, then C of phi tilde is strictly positive. And finally, even more, let's say, technical assumption, but why I was a bit exhaustive here is the aim is to say that if you have only these 7 properties, if you are able to construct a map with these 7 properties, then you are able to get the non-squeezing. This is the only axiomatic properties you need to get the non-squeezing I mentioned, so theorem A. So, and the last a bit technical property is, okay, you have MK, which is, so M is a covering over MK. So if you have a contact isotopy in MK, you can lift it to a contact isotopy. So starting at the identity, you can lift it to a contact isotopy of M. And this is the map I'm talking about here, this lift. And then you have some kind of compatibility. So C of phi tilde. So if you are in the case of the sphere, C of phi tilde it's better than it is an element of the spectrum of phi tilde. It's even an element of the spectrum of the lift of phi tilde to the sphere. Okay. And this is for the sphere. And if you are in a strongly orderable prequantization, let's say the equivalent statement, the one I use in the same way to get my result, is the following. So C of phi tilde is greater than C of its lift. Okay, a bit technical, but...
So I have a question about this action spectrum. Again, pretty basic. I guess the easiest example of these contact isotopies in this prequantization construction would be to take a Hamiltonian flow on the base and then lift it via the holonomy map of the connection, right, to the circle bobble. And then these translated points are just, points where you flow for time 1 and you come back to the same fiber.
Yeah.
So they basically just correspond to 1 periodic points of the Hamiltonian on the base.
Yeah.
And then, fixed points to the time 1. So then these fixed points have some natural, like there's an action functional. And so I was wondering how the action functional relates to the translation.
It's the same.
It's the exact same. Okay.
Yeah.
I see. So in that case, the translation spectrum there is just the same as the action spectrum.
Yeah, I think at least at least I think I know how to make it very precise when you take exact symplectic manifold downstairs. If you don't take exact symplectic manifold, yes, I think also you can make it precise, but
Yeah, I mean, probably you want it to be exact because otherwise you have to do cappings.
yeah, exactly.
Yeah, so-
And the capping, I think, is just like going along the red flow more and more. And but yes, I think it's a good interpretation of translation of translated points. Yeah.
So are these like let's say a contact version of like the Hofer-Zander capacity or something? Or are they like, or yeah, if you took CK of one of these, lifts of a Hamiltonian isotopy, would you recover some
CK of the lift. Actually,
Hofer capacity or something?
okay. So actually, for the case of the sphere, I will give an idea of the construction just after that, and I think it looks more like, I don't know, maybe it's not very well known, this kind of techniques, but it's a capacity that I think the first one who constructed it was David Terre using Giventhal's nonlinear Maslov index. So he was able to construct some action selectors for Hamiltonian isotopy of CPN. So, and then this would be let's say the generalization of this David Terre construction.
Okay.
So more using generating functions. So the link with Hofer-Zander capacity is not really clear. And it would be interesting, but even Hofer-Zander capacity, I'm not even sure how to make sense in the context of contact geometry, but for sure it will be interesting to.
Oh yeah, I wasn't even suggesting anything along those lines.
Yeah.
I was just wondering if these reduced to something that I know about. So you're saying they're reduced to this nonlinear Maslov.
So yeah, for the sphere, and then for strongly orderable prequantization, it relies on this order. And then this order also is a bit mysterious, how this order is linked to over invariant coming from Floer homology or things like that.
Yeah.
So for the moment, it's still a bit unclear. But I think all these things are a bit linked, of course, but to make the precise link is a bit, not so easy. So yes, for the sphere, actually, it comes from the nonlinear Maslov index. So how we construct, so now I just give a quick idea on how we construct this kind of spectral selectors for length spaces. So it uses, as I said, the Giventhal's nonlinear Maslov index. And maybe the heuristic around the Giventhal's nonlinear Maslov index, you can think of the space of all contactomorphism as an infinite dimensional space. And then you look at a hypersurface in this space, which is the hypersurface consisting of contactomorphism having a discriminant point. So it is like a hypersurface in this space. And then when you look at a contact isotopy, actually it counts how many times you cross this hypersurface with multiplicity. So this is a bit heuristic, and you can make it formal by some maybe construction I will mention using generating function techniques. But at least I give two properties of the nonlinear Maslov index. Okay, so you take a path inside con tilde. Then if at some time S1, the Giventhal's nonlinear Maslov index is different than the Giventhal's nonlinear Maslov index at the time S2, it implies that there exists a time U such that phi tilde of U has a discriminant. Okay, this was a bit what I was saying. When the Maslov Giventhal, when it jumps, it means that you have a discriminant point. And also, okay, this map, if you take any phi tilde, you compose it with the red flow, Okay, I put minus t here just for technical reason. But if you take minus t, then it's non-decreasing. So if you look at t here, it will be a non-decreasing map. And that goes to minus infinity when t goes to infinity and plus infinity when t goes to minus infinity. And then how we construct our spectral selector, we just take the smallest t such that when you compose phi tilde with the red flow at time minus t, you get some negative number. And so first, because when t is very small, it is plus infinity. So this number is finite. Okay. And moreover, it jumps from positive to negative. So let's say you have t here. So exactly when you get a discriminant point. So this map having a discriminant point is exactly saying that this map, phi tilde, has a translation point of translation t. Okay, this is why this map is a spectral selector. Okay. But then you have to check that it satisfies all the theorem, all the assumption of theorem C, and it requires some work, of course, but yeah, this is how we construct it. And maybe I don't have enough time to say, but yes, the given task nonlinear massive of the index uses generating function techniques. But yeah, maybe I move, if you don't have any question, maybe I move to idea of the construction of this map for strongly orderable prequantization. Okay, so here the construction will be, yeah, completely different a priori. So you start with a contact manifold, and you can associate to it a bigger contact manifold, m times n times r, with the kernel of this one form, alpha 2 minus exponential theta alpha 1, where alpha 2 is just alpha on the second coordinate and alpha 1 alpha on the first coordinate. And then if you take a contactomorphism, you can associate to it a Legendrienne of m times r by looking at its contact graph, okay, which is the set x, phi of x, and then g of x. So in the last coordinate, I put the conformal factor of phi t. So you get a Legendrienne, so a submanifold which is everywhere tangent to the contact distribution. So if you have a whole contact isotopy, you have an isotopy of Legendriennes. And to any Legendrienne isotopy, you can also associate to it its contact Hamiltonian. So you take any parametrization phi t of your Legendrienne isotopy, you look at the speed of this contact isotopy, and you contract the speed, you contract beta with the speed, you get a function ht. And actually, ht does not depend on this parametrization because lambda t was Legendrienne, so everywhere tangent to the distribution. So you get a function. And then I call, this is just for this talk, this is not it's a classic convention. I will talk about the positive length of a contact isotopy to be the maximum of this Hamiltonian function. And then C of contact isotopy, so homotopy class of a contact isotopy, will be the smallest length of all Legendrienne isotopies that are Legendrienne isotopic to this isotopy of graph. Okay, so this number could be minus infinity. And the theorem is the following. Actually, if M is strongly orderable, so I didn't say what is strongly orderable, but now I say it finally. So I say that a contact manifold is strongly orderable if you don't have any loop of Legendrienne that is at the same time contractible and whose length is negative. So, and a more geometric way to think about that is that you don't have any contractible loop of Legendrienne whose speed is transverse to the contact distribution. you cannot find this kind of contractible loop. Okay? Then this map satisfies all the assumptions of theorem C. And of course, finding obstruction to existence of such kind of loop, it's really harder usually. And as I said, for example, if you take unitary cotangent bundle, then they are strongly orderable, but then you have to use hard techniques. You have to use the fact that the symplectic homology of the Liouville filling does not vanish. So to find obstruction to existence of such kind of loop is not easy. But once you have it, then you can derive very interesting numbers, okay, that are spectral. This we showed with Simonyi that this number will be an element in the spectrum. Okay. And I don't know, maybe I have some time left. And
Yeah, you have a few minutes.
okay. So, but then the proof, I think, is okay. Yeah, maybe that's good. I didn't say. I said heuristically how I define this capacity, but I didn't give a concrete definition. So what I said heuristically is that the capacity of a domain U measures how much a contact isotopy supported in U can translate a point in the right direction. But now with all this theorem C, we can give a concrete definition of this. So I will talk about the capacity of U to be the supremum of the spectral selector of phi tilde, such that phi tilde is supported in U. Okay. And then theorem B again. I claimed that by defining it like this, so the first assumption is trivial, because if U is a subset of V, then you take any phi tilde which is supported in U, it will be supported in V. And then it remains to prove these three properties. This property is, let's say, it's now a bit a classical argument. It's the first time it was shown was by Scheller-Sandon in some sense. And then we have these to estimate, and these also use this one, so the upper bound, use energy capacity inequality, and this one is an explicit construction. So maybe in 2 minutes, I don't know how much time left I have.
Yeah, 2 minutes.
Okay, so maybe I give. So for this one, yeah, the fact that the 2 pi over k integer part is invariant by contactomorphism, it used the fact that the 2 pi over k integer part of phi tilde is conjugation invariant. Okay, and this actually the first one who had this kind of lemma was Scheller-Sandon, and it's not very hard, but maybe if you have questions, it's a very easy argument, but maybe I can. So, and then to have the estimate that the capacity of the ball of radius r is less than pi r square, what I use is a capacity, energy capacity inequality, a bit as in the symplectic setting, just that here I say that contactomorphism displays a domain if it displays all the Reb orbit of this domain. Okay, so it displays the domain, but also its orbit under the Reb flow. And then it's easy to show, and the argument goes a bit like in symplectic geometry, that if psi tilde alpha displays a domain U, then the capacity of U will be less than the energy of psi. So here what I call energy of psi is this number. And if moreover psi is strictly is a path of strict contactomorphism, then I have this. And yes, the argument goes a bit like in symplectic geometry. If phi tilde is supported in U and psi tilde displaces all the orbit of U, then the spectrum of psi phi is equal to the spectrum of psi. And so you can argue by continuity and nowhere density of the spectrum that C of psi phi has to be equal to C of psi. And then you just use triangle inequality to get that C of phi will be less than C of what you want. Okay, and so then it's not so hard to displace the ball by a contactomorphism whose energy is not too big. Okay, so this is the idea on how to get the lower bound, the upper bound, sorry. So using this energy capacity inequality, and to get the upper bound, you do also an explicit construction. I think the first time I've seen this construction was by Helmut Hofer in his book. So you lift everything to the prequantization. Actually, you can find. So I don't know if I can explain it well, but yes, it's an explicit construction. So let's say in symplectic setting, it's not hard to find in a ball of radius r, you take an Hamiltonian function in this ball that is radial. So what I mean by radial is like it depends only on the radius of x, so the norm of x. So f is just, okay, maybe I erase a bit. So f is just a function. And then the flow of this Hamiltonian function will be just a rotation. So exponential 2i. Rotation of speed f prime. And so in a ball of radius r, let's say here pi r square. So if your speed is less than pi, if f prime is less than pi, then you don't have any fixed point. Okay, because you have a rotation that does not close. And here, okay, your slope here is exactly, I think, minus pi. But then, so this one will have a closed orbit, but then you can take for epsilon small, you take something that has a bit smaller slope than pi. So you don't have any periodic orbit in the center. And as Rolly said, there is a link between translated point and periodic orbit. So you can, so if you lift, okay, I go very bad, but if you lift this this symplectomorphism to the prequantization, you will have a translated point only here and here. And the translation here will be exactly of pi r square minus epsilon, and the translation here exactly of translation 0. So it's easy to construct this kind of contactomorphism in your first prequantization. And then, you argue using spectrum that the capacity of the ball, so then the capacity of this contactomorphism, so you know that it is non-degenerate, it cannot go on this red line, on this blue line, if we have to go on this red line, and you can deduce that the capacity is of this contactomorphism is greater than pi r square. And, okay, so sorry, I a bit over time, but thank you for your attention.
Okay. Questions?
Like this square root of 3 just because you need to adjust this, like just for this translation that you put to the center. So maybe you can make it smaller if you can find maybe better displacement.
Actually, this square root of 3. So here in this picture, it's even worse than square root of 3. I think here I'm dividing by 2. So, okay, because this square root of 3, I just need this little r to be small enough with respect to this big ball so that I have enough room to displace it. And here, this embedding, this translation is not the best one. This, because here, I think with this picture, I would be able to go with A divided by 2. And also this translation has energy 4r squared. 4r squared, of course, is greater than pi r squared. But yes, as you say, maybe this can be done a bit better. I think the square root of 3, if you find better displacement, so if you are a bit more clever about the displacement, I think this pi r square is the best you can do there. But maybe, yes, this, I can do it for R that is even bigger in this big board. Okay.
For the proof from theorem C to B, I got a little lost, but you wanted a loop that's, what was the loop that you want? And that's only for sphere quotient or it's for both? Like, what was it?
Okay, I'm not sure. So you are talking about the loop of Legendrienne? Yeah. Yeah, okay. So, yes, sorry, I was very too quick here because here it's maybe the most interesting thing and I said it. So, no, here it's not for the sphere. So, actually, the theorem that I've written here, like theorem A in one theorem, actually in my paper, I've written it as 2 theorems. So, one theorem for the sphere and length spaces and one theorem for strongly orderable quantization. So, for the moment, I think it's 2 separate words. Maybe they are the same. So here it's not for the sphere. And what was your?
Oh, could you just explain this loop again?
Okay. So I think this is the. So I think this is the definition of strongly orderable. I take n psi, a manifold. I say that it is strongly orderable if when I look, at this bigger contact manifold, let's say with the contact distribution big psi, in this big contact manifold, I have a special Legendrienne, let's say, which is given by the diagonal. So I say that this contact manifold is strongly orderable if I take any Legendrienne isotopy lambda t, which is a loop, so lambda 0. Okay, so this is m times r, a Legendrienne isotopy such that lambda 0 is equal to lambda 1 is equal to this diagonal. If I take, so it is strongly orderable if there does not exist loops that are contractible. Okay, such kind of loop, they cannot be at the same time contractible and everywhere transverse to the contact distribution. Okay, Legendrienne or tangent to contact distribution. When I say transverse is when I look at the speed of the loop. Okay, so you have your contact distribution and then you have a, I don't know how, it's hard to draw, but you have contact, you look at the path of Legendrienne, you look at the speed of the path, and this speed cannot be at the same time transverse to your contact distribution and the loop contractible. If you don't have this kind of contractible loop, then you are strongly orderable. And actually, it's a whole topic, this orderability. And here I stated it just in 2 sentences. But once you don't have this kind of loop, actually, you have a partial order on the space of Legendrienne, or at least on the space of universal cover of Legendrienne. And you have also So usually I denote it by L tilde delta. So the universal cover of the space of Legendre that are isotopic to delta, this diagonal. And when you have the partial order on this, you have also a partial order on the group of contactomorphism itself. Actually, it's stronger to have partial order here because when you look at the graph of contactomorphism, actually you get Legendrian. So if you don't have contractible loop of Legendrian which are positive, a fortiori you don't have a loop of contactomorphism that are contractible and positive, and then you have partial order, and yes.
Yes, thanks, speaker again.